All right, so last time we started in on mass spectrometry. We went over a little bit about instrumentation, just a simple mass spectrometer, what we call a single sector instrument. Remember, within the instrument we need to first form ions, and we only analyze the ions. The only method we've looked at so far is called electron impact ionization. Right? And this is where we essentially shoot the molecule with an electron beam. When the molecules get hit by that electron, then it excites the molecule, and that molecule, among other things, will eject an electron to form a radical cation. Okay, so we start with some molecule, we shoot it with electrons, and it ejects an electron to form this molecular ion. That molecular ion can then fragment to give fragment ions. Okay, so we get a mixture of these ions, and those ions then need to be separated, and so they're separated by their deflection in a magnetic field, and then they're detected and counted, and so our spectrum really shows mass to charge ratio on the x-axis and abundance on the y-axis. Okay, remember the tallest peak is called the base peak. The peak that includes all of the atoms is the molecular ion. All right, so we finished off last time starting to talk about how different isotopes of atoms can give us some information. All right, and we talked about, I don't think I brought that, well, I think we'll get back to the same table that we used before. But we already know that C13 is an isotope of carbon. That's 1.1%. That's not a big percentage, but we can see it, and we'll talk about today how we could actually use those isotope ratios to determine molecular formula and to figure out how many carbons there are. The other two isotopes or elements that are really easy to pick out were chlorine and bromine. All right, so let's just start off by spectra that have those isotopes. All right, so here is just I don't know how many carbons, 1, 2, 3, 4, 5, 6, 1 bromohexane. All right, and so the things that we can easily see are here at 135 and at 164. So we have 164 and 166, right? So this is the M and the M plus 2. And we see that these are in roughly a 1-to-1 ratio, and so that tells us that bromine is present in the molecule. Okay, because a loss of 2 is not a common loss, right? So it would be uncommon that 166 was just the molecular ion and it's losing 2 to give 164, right? So both of those together, in fact, well, we can't see the 164 and 166 that well because it's low abundance, but all of that is the molecular ion. All right. We notice that 135 and 137 are fragment ions. Right? Notice we've gone from an even mass to an odd mass because we've gone from an odd electron ion to an even electron ion. All right, and we have no nitrogens to mess this up. So we can tell that 135, 137, the chlorine or the bromine is still present in that ion. But if we look at any of the, well, there's bromine is still present in this ion right here, but once we get down to 85, then we've lost the bromine. In fact, I think if we go from 164 minus 79, right, then we get 85. Or if we do 166 minus the 81 isotope, we also get 85. All right, so those ions are going to 85, and this is essentially the M minus the bromine. Okay, and then we notice that these other ions we've seen before, this is probably just propyl.
You said 166 minus what?
81.
81.
All of these other ones do not contain bromine. All right. What about this one down here?
Looks like it. Well,
Well, can it?
Doesn't weigh enough.
It doesn't weigh enough, right? The
yeah,
mass
you
is
gotta-
too small.
gotta think about that.
Yeah.
Right.
Trick question. Yeah, so that looks like 27 and 29. Yeah. So like I said before, there's oftentimes some ions down there that we're going to have a hard time, saying what they're formed from. And we're not so much into the fragmentation right now. We're mostly looking at the ions and their isotope patterns. Okay? All right, so the next structure, we see 156 and 158, and these are in a roughly 3-to-1 ratio. And so this tells us that there's chlorine in the molecule. And likely, none of the other fragments contain chlorine, right? So if we took, 156, and chlorine is chlorine 35 and chlorine 37, those are the two isotopes.
121, 119.
Huh?
121, 119.
What's 121 and
Sorry,
1?
I just subtracted them.
Oh, is it? Well, no, yeah, okay, minus 30. Sorry, you were too fast for me. So 121, I guess there's a tiny one right there. But the other one, 158, we would be subtracting 37, right? And so those should both give the same thing. So the direct just loss of chlorine itself gives a very small ion. Okay, so that's not really a favored fragmentation in this molecule.
But the other peaks don't contain chlorine, you said, correct?
Correct. Because why can we tell that?
Because of the ratios, but if we don't lose a chlorine, like if it's not favorable to lose it, it's not favorable just to lose.
To only lose just the chlorine, right? So if we take, say, 35 plus
Carbon or something.
well, we wouldn't just include just a carbon, right? It would be more likely to include a CH2 group or something like that, right? It's got to be, like we talked about last time, it's got to be some logical loss. So if we subtracted, let's say we included another 14 for a CH2 in here, let's subtract another 14. So that'd be 11 minus 4 is 7, 107. Right, so this might be the loss of something like CH2Cl. Okay. Main thing here, though, is by looking at this molecular ion, we see the 3-to-1 ratio that, like, sets off the bells on our head. Oh, there's chlorine.
So could we do a CH2Cl loss for 94? And that's how you could build a molecule?
Well, maybe, yeah. We'll go into that in a little bit. We'll talk about the fragmentation.
Oh, okay.
Okay, so we'll get to that in a minute. All right. Okay, so here's just some different patterns that we could have for different combinations of halogens. Right? So the only ones we've really talked about so far is chlorine right here gives us a 3-to-1 ratio, and bromine gives a 1-to-1 ratio. But if we have 2 bromines, right, then we essentially get, looks like a triplet from NMR, right? And so basically what we have is we have one possibility that we have 2 bromine 79s, right? And then we have a bromine 79 and a bromine 81, but we also have the possibility to have it reversed, right? So bromine 81 and bromine 79. So there's 2 possibilities of getting that combination. Yes?
Is this BR2 or is this just 2 BRs in a molecule?
Just 2 BRs in a molecule.
It's not BR2. It's
Well, BR2 would look like that as well.
but it could just be.
Right, we could just have a dibromide
You
compound.
could have a dichlorinated molecule, a dibrominated molecule that wouldn't have a 3-to-1 ratio.
Right. Right, so up here, so this is bromine 2, so and then we have bromine 81 and bromine 81, right? And so this gives us basically this 1 to 2-to-1 ratio. And they're M plus 2, M plus 4. Okay? Up here is what would be if we had 2 chlorines. Right? So the pattern gets more complicated. And look at as we go farther down, bromine 3, you know, they have all of these different patterns. Okay. So there's actually, I think, I'll have to look back. I may actually have some links on our Canvas page. You know, there's programs that you can put in a molecular formula and it'll calculate out what the isotope pattern would look like.
Very helpful.
Yeah, so especially things like this, you know, especially with those chlorines and everything in there, it's a little hard to tell. The one thing that we can tell that these are coming from a mixture of halogens is that all of these peaks are always 2 mass units apart. Right? All right, so like I said, the C13, though, is important since we're doing organic chemistry for determining the number of carbons there are in the molecule. All right, so we can do this for any ion. It doesn't have to be the molecular ion. All right, and what we can do, we can just use this formula here that says that the number of carbons in the molecule equals the relative intensity of the M plus 1 peak divided by 0.011, which is 1.1%, times the relative intensity of the M peak. Okay, so if we were going to do this, we would say that the number of carbons equals the relative intensity of the M plus 1, so this is at 11%. So we have 11 divided by 0.011 times the M peak, this is M plus 1, and this is M, is at 100%. Times 100. All right, so if we do this math, we essentially end up with 11 over 1.1, right? 100 times 0.011 equals 10. Okay? And so essentially what we see is that m plus 1 should be 1.1% for each carbon in the molecule. Because there's an independent probability that each carbon would be 1.1, there's independent 1.1% for each carbon that it's C13.
They're not adding it.
Right, well, we just add them up here. So if there's one carbon, then it should be 1.1%. You know, if there's 5, then it should be 5.5%.
Okay.
Right? If it's 10, then it's 11%. Okay?
So, if you had, say, like heteroatoms,
Mm-hmm.
nitrogen, oxygen, a metal perhaps.
Right.
I mean, could you do something like this, or do you have to remove those atoms first before you do that?
Well, it depends on whether those other atoms contribute to the intensity of the m plus 1 peak.
Yeah, that's true.
Okay? So some of them do, some of them, like bromine or chlorine, really are only doing the m plus 2.
The m plus 1 would be left alone.
Yes.
Okay.
And cobalt isn't.
Okay? And we're going to look at some other ones now. I don't
Okay.
really know about the metals.
Yeah, that's what I was like. I was like, this
Cobalt
could be
doesn't
useful.
have one. Copper does.
Yeah, that's what I was gonna say. So it probably won't be.
Well, yeah,
Still,
so
it's still interesting.
yeah, I think this isn't always practical.
Yeah. No.
Just that it's extremely.
But I think it's good for us to understand.
That's why I was curious about the heteroatom as well.
Yeah. Well, well, let's look here. I've got that.
Yeah, right.
Okay, so if we look at this, so we're going to see, some contributions from, carbon, of course, we were just talking about, some contribution from deuterium, right? Nitrogen has a contribution, oxygen very small, silicon has a pretty big contribution to that, and sulfur can also. So all of these have some contribution to the, am I doing this right? The m plus 1.
Yeah.
Okay? So what we need to be able to do if we're really using this is that notice that, say, oxygen has a bigger contribution to m plus 2. Right? So if we see the presence of oxygen based upon its m plus 2, we can then subtract its m plus 1 contribution as well. Okay? And the same for silicon and sulfur. All right, so I'm going to show you the A method. Like I said, I don't know how practical this is anymore, but we'll just do a couple of examples of how you can actually calculate out a molecular formula based upon these isotope patterns. And this was a big deal. When I took this class, of course, a long time ago, the mass spectrometry portion of the class was taught by Fred McClafferty. And he's like one of the gods of mass spectrometry. We'll talk about this. Yeah, fragmentation is called the McClafferty rearrangement, So, and we worked straight out of the book that he wrote and all this kind of stuff. And yeah.
Is there a rounding rule for the isotope of carbon? Sorry, I just tried it with a real mass spec, and then I got 12.987.
Uh-huh.
Is there a rounding?
Well, I don't know it's necessarily rounding one way or the other, but there's certainly experimental error and uncertainty. And so you're hoping to calculate these within maybe 10% or something like that.
Same thing would be like 0.9 or 0.1.
Right, yeah, you're gonna round, yeah.
0.7,
Sure.
0.4.
Yeah, it doesn't come out exact.
Yeah.
Experimental error just doesn't really allow that. And plus, well, here here's some of the things we got to consider up here is that the ion that we're looking for must be chemically pure, right? So you can't have a mixture of compounds, or you can't have more than one ion that has the same mass.
Because if it's a mixture, but there's only one ion with that mass, that's fine. Correct?
Right, if there was a mixture of compounds, but you're looking at an ion and that ion is chemically pure, then you could do this. But if you had, you could have two ions with different formulas that coincidentally have the same mass, right? And then that would screw this all up, right? The other things, as we've already talked about, I guess we've gone through these things, that our ions are actually clusters of peaks, right? Because of these isotopes. And what else was I going to say there? Yeah, the main thing is it's got to be pure, and so the ion has to be separated from other ions. Or the other thing you couldn't have is one ion at, say, mass, 85, and then another ion that was at 88, right? That would be on top of your M+1. So you can't have overlapping isotope clusters. And you have to have good signal to noise. So if your ions are very weak, then you would have too much noise, and that's going to impact the abundances. All right, so here's kind of the requirements. Like I said, they've got to be strong ions. We have to have a high signal to noise, and we need to have some type of printout of the ion abundances, right? And so here's the strategy. We choose any ion that's free of interfering peaks, right? Could be the molecular ion, could be a fragment ion. We're going to write down the masses and the abundances of these three peaks, right? The main peak with the most abundant isotopes, the M+1, and the M+2. Then what we have to do is that we have to normalize that M+ peak to 100%. The example that I showed you was already at 100%, right? But when we say that the carbon peak is 1.1% for every carbon, that's relative to 100%, right? So if that M peak was only at 50%, then the carbon peak would be half as big as well, right, on the absolute abundance printout. Once we've done that, we first look for M+2 isotopes, so chlorine, bromine, silicon, sulfur, and silicon. We either account for those or we rule them out. Then we determine the number of carbons based upon the M+1, and then we look for oxygens after that. And then after that, we just add hydrogens, making up the difference in mass. Right? Whatever we have left over have to be hydrogens. Okay, so here's a couple of tables. These are from McLafferty's book. And these are this one is essentially just like we saw on that other one. It gives us mass percents for the different isotopes and what type of element they're considered. M+1. He uses A's instead of M's here. I guess he uses M's for molecular ions and A for other ions. Okay, and another table is this one, which tells us how big that M+1 or A+1 and the A+2 peaks should be for the number of carbons. All right, so notice as we go down here, you know, the +1 peak just increases by 1.1 each time. The A+2, which if we only have one carbon, is very small and it has a small contribution, but as we get a lot of carbons, it starts to make a considerable or a measurable contribution to the M+2 peak. All right, and so this calculates them all the way out. Look at it, if we go all the way out to this 100 carbons, look at that, the M+1 peak, no, the M+1 peak, 110, does that say it's actually bigger than the M peak? Huh, I don't know. Okay, so let's look at a simple one here and see how we can do this. All right, so we've already written out, this is essentially M+1, M+2. All right, and in this case, and then we write out the peak heights as well. In this one, we're already looking at a base peak, so it's already 100%. Okay, so then what we do, so essentially these two things are already done. All right, now we're going to look for M+2. Okay, so we look back at our table and we see that M+2 is 0.451. And so we look for what other groups, chlorine, bromine, sulfur, or silicon.
The M+2 is 1 point,
It's 0.451.
is 0.451.
Right.
It's written down on next to it. So.
Okay, so then,
Yeah, it's right here.
mhm.
Yeah.
So we look down at those, the M+2 elements, and we see what we could fit in there. Chlorine, bromine, sulfur, silicon. Will any of those fit?
So we look at A+2 on table 2.1.
Yep.
And we threw in 2.
We're looking for silicon, sulfur, chlorine, and bromine.
Any of those fit?
None of those will fit, right? And so, if none of those fit, we already checked that. Now we go and we look for the number of carbons. All right, so now we're going to look at the M+1 peak. And we see that it's 3.39. So we can, this one's easy enough, but we can look at that table 2.2. 3.3, right? So how many carbons? 3 carbons, right? So I'm just going to write C3 up here. The M would be 100% for contribution. This would be 3.3. And then it says for 3 carbons, the A+2 contribution is 0.04. Okay? So then, you know, what we can do, we can either do this just kind of in our head, or we could, you know, subtract these. We want to see how much abundance at the A+1 and A+2 is left unaccounted for. Right? So if we, say, subtracted these two, we'd see we have 0.411 left over. Right, and we have 0.091 left over for the M+1. Okay, so now, so we figured out the number of carbons. Now we're going to see if we can add any oxygens in. How many? 2, right? Because if we look for oxygen on that table, 2.1, oxygen contributes 0.2 for the A plus 2. And we have 0.4 left over. So we can have 2 oxygens. We always go 100% for the top one. 2 times the A plus 1, 0.04 for the A plus 1, so 0.08. And 0.4 for the A plus 2. Okay, so now what we need to do is add up our masses as well. So we have C3O2. So what does that add up to? Huh? Okay, so that adds up to 68, right? And we have 4 mass units left, so we have H4. Right? We can write these in as well if we want to see how they actually all add up. So, oh well, 4 hydrogens we'd have to. The A plus 1 is 4 times 0.015. I don't know if I wrote those numbers down here. I didn't write those down. Okay, so our formula should be C3H4O2. All right, everybody follow that? Okay, so let's try another one. All right, so this one also has it set at 100, at least for the, oh, let's see, the peak at 94. So what do we see first? Bromine, right? And so we could put in a bromine, so that would be 100, and then this would be 98. Okay, is what we'd get off the table, I believe. 198. So our mass is only, well, so then we got to look for the number of carbons. All right, so how many carbons do we have? Just 1 carbon, right? Because that's 1.1. All right, so then we got to add up our masses. So 79 and 12, right, gives us 91. We got to go to 94. So we have H3. And so it's just bromomethane. All right, let's do another. I don't know how many do I get here. I get 2 more. Okay, so all of these so far, though, have all been set at 100, so we haven't had to normalize anything. So, what's the first step here? We've got the abundances all written out. M plus or A plus 2. So, what can fit?
Where are carbons?
Yeah, good question.
I don't know.
The M plus 1 is really small.
Okay, so what's the first thing we do again?
So we're looking to.
A plus 2.
Okay, so we look at the silicon, chlorine.
Yeah, so we got a 5%. So we'll try to pick out the biggest one that can actually fit in there. Silicon is 3.4. Sulfur is 4.4. Right? So I think we'd try to put a sulfur in there first. 100. Let's see, for sulfur, 0.8 for the A plus 1. And 4.4. Okay, so we only have 0.1 left for the A plus 1, and we have 0.6 left for the A plus 2. So what about carbons? None, right?
You have 3 oxygens or something?
Well, it looks like we could fit 3 oxygens in there.
3, yeah.
Can we fit it in mass-wise?
So 32 plus, how much is sulfur?
32.
Oh, so 64.
Yeah. So there has to be 2 oxygens,
Yeah.
right? So it's a little off on the A plus 2. So this would be sulfur dioxide.
Oh, so I was right.
Mhm.
Okay.
Yep, no carbons.
You had 0.4 for A plus 2, and you have 0.08 for M plus 1 for O2.
Oh, for the O2, right, we would have 0.08, yep,
And
0.08, and 0.4.
and we know that that's okay too because of the mass, because we could go over by 0.2.
Right. But we
Yeah.
can't go over by mass.
So we tried that and realized, oh, it's
Yeah, exactly.
Okay.
Yep,
And that's where the instrumentation error and experimental error.
yep,
Okay.
yep.
I think they should be 3 oxygen.
Right, but if we add 3 oxygens, if we have SO3, what's the molecular mass? Right, it would be,
It's F80.
yeah, it would be 80. So that's too high. Right, so even though the A plus 2 would fit perfectly,
Yeah.
the mass doesn't fit, right? So it's always going to be a little off. I don't know what we're off here, but I think the rule was we're hoping to get within plus or minus 10% on those abundances. Okay? One that has a few more ions in here.
You make me very nervous to put mass back up on my seminar.
Well, you know, not.
But it's yes, I know. It's slightly. We're looking at it for
It's
something different.
APCI.
You're mostly just looking, in that case, at the molecular ion and, you know, or,
Yeah, we'll see what you say.
yeah. All right, so let's do the molecular ion. Okay, so we look down this big table, and so here's 154 to 156. Okay, so I'm going to write these out. 154, 155, 156, and these are at 100% and 9.8 and 5.1. Okay, so the first thing we do is look for the A plus 2. And it looks like I would like to include those on this one. So again, 5.1, the highest one we could get was sulfur. Right, so that's 100, and and then 0.8 and 4.4.
8 carbons.
Right? And so then we have 9.0 left over, right? So the closest we can get to that on the number of carbons is 8. Exactly right. C8. So this would be 100, this would be 8.8, and if we look at that table 2.2 for 8 carbons, 0.34.
Oh, that's nice.
Okay. Then we should look for the presence of oxygen. So we have to add these up, right? So this is 4.74. So what do you think? Can we fit some oxygens in there?
Potentially 1 to 2, 1 to 2 maybe.
Okay. We can try, you know, it's kind of a trial
A
and
little higher, yeah.
yeah, so we could try, what if we tried 2? So that would be 0.0, this would be 0.08, and this would be 0.4. So that would get us just 5.14, right? Just barely above. So what about if we add up the masses? I don't have a calculator for that one.
160.
160. Okay, so it's too high. We can't do that. So let's take off one of those oxygens, try 1 oxygen. So this is 0.04, 0.2. Okay, so now we have C8. How many, what's the mass of that one then? Hmm?
Yeah, 96 for
96, what?
96 for 8 carbons.
Okay, what about if we add a sulfur and an oxygen?
It was 160, right?
144.
Previously, so
Yeah.
144.
144, yeah.
144, okay. And so how many hydrogens do we have? 10 H10. So C8 H10 SO. All right. So let's go to another ion. Let's look at this one down here. All right, so that's at 139 to 141. Okay, so we're going to do the same thing. 139, 140, 141, and these are only at 32, 2.7, and 0.8. All right, so in this case, we have to normalize these to 100%. Right, so we're just going to take 100 divided by 32. Hmm? Oh, did I do it right? Oh, yeah, you're right. Thanks. So, oops, that's not the right tool. 2.7, 1.6. I went down one too many. All right, so we have to normalize. So we divide 100 by 32, we get a factor, and we multiply all these by that, right? So this is going to be normalized. This has to go up to 100. And then I did these before. This goes up to 8.44, and this goes to 5.0. Okay, so now we can do the same thing again, right? But we got to make sure to do the normalization because all these percents abundances are relative to 100. Okay, so it looks like we still have sulfur, right? So that's 100, 0.8, 4.4. How many carbons?
7.
7. So we subtract 8.44, well, minus 0.8, right? So we get like 7, what is it, 0.64. So there can only be 7 carbons now. Look on the table that, oh, I didn't write all those out. Oh, I could look at the table. 7.7 and what?
0.25.
0.25.
Maybe 8.5 and 4.65.
Okay. All right, so what do we, oh yeah, so then what do we got to look for?
Oxygen.
Oxygen.
6.5, so you could have
1 oxygen, right? So that's 100, 0.4, 0.2. And then how many hydrogens do we have left over?
We have to find the mass, don't we?
Yep.
See how many moves.
Yep, and we're looking for the difference in mass now. 7,
So 132, and you go 139. Yeah, so
H7. So C7, H7, SO. All right, so does this make sense? Right, because for one thing, if we come up with a formula for a molecular ion, and we look at a fragment ion, obviously we can't have any more atoms of any element than we started out with, right? We couldn't start with 1 oxygen here and end up with 2 oxygens over here. Right? It has to be a fragment. It has to start from there.
These
So
don't react with each other in this environment, correct?
right. Yeah, there should be no reactions in this technique. Okay? Because it's done under vacuum, and so the molecules are kind of far apart. There should really be no bimolecular reactions. All right, so chemically, does this make sense? What have we changed in our formula? Right, we've lost a CH3. We've lost a mass of 15. Okay? So you could do this, and whenever you have, like we could probably do.
Does it tell you anything about the proximity of that methyl to anything else? The ease in which it was cleaved?
Perhaps.
Does it tell you anything, or?
Yeah, maybe.
Okay.
You'd have to know.
Well, there has to be a cleavage mechanism that would allow that methyl group to come off.
Like, is it more likely to be next to a sulfur or an oxygen at the end of a carbon chain, not next to one of those?
Well, let's wait until we're going to talk about those cleavage mechanisms.
Okay, sorry.
Yeah. So if you had like if you just had some carbon chain it's usually there's going to be some functional groups, and like we talked about before, it's usually that ionization takes place on either the non-bonding electrons or on pi bonds, and so it's always going to be the site of ionization which dictates cleavage, right? Because the mechanism for cleavage is going to start from this radical cation, right? Just not randomly anywhere. And since cleavage at just a sigma bond out in an alkyl chain is kind of disfavored if there's other places to ionize. All right, so this is kind of a cumbersome way to do this, but I think it's interesting to know how these isotopes work, to come up with these patterns, and but don't do it. Dang. In real life, we use what's called high resolution mass spectrometry. And so what this relies upon is that the masses of the different atoms are not all just unit masses, right? The only one that is carbon. So carbon 12 is set at 12.00000. But maybe we talked about this before, but if we look at the atomic weight on the periodic table, carbon says 12.011. Right? So how do they come up with these masses on the...
The sum of the relative isotope.
Right, it's like it's a weighted average, right? And so when we do mass spectrometry, we can't use the periodic table, right? Because this is averaging from the different isotopes that are there. So this table shows us, so here's atomic weights from off the periodic table, but these are weighted averages. Here's the masses of the actual isotopes.
We just picked one to be standard.
What?
We as humans just picked one to be standard, and we decided carbon was going to be standard at 12.
I guess so,
Okay.
yeah.
It's
And
the highest one, though, right? The highest one. Anyway, sorry.
It's the most important one, right?
For us.
Organic chemistry for everybody. We're carbon-based.
Yeah.
Or carbon hydrogen based.
Maybe. I know, they could have just picked a unit number at the bottom and moved up from there. But, so the bottom line here is, notice that it's only carbon that comes out exact. So if we can measure a mass beyond just an integer value out a number of decimal places, then we can start to tell molecular formula from the actual mass measurement. Okay, because there might be more than one formula that comes up, that we could come up with, that matches a unit mass, but if you measure it out to 4 decimal places, some of those won't fit. Okay?
And this is, do you still use electron impact here, or is this when we start coming down?
You can use any of the techniques here.
Okay.
You just have to have, it more depends upon the ion separation technique. Okay, so when they separate the ions, you know, whether they're using the magnetic field or some technique to separate them, that technique needs to be able to really separate them with good resolution.
Okay. And is the entire device called a mass spec, or is the injection part and the mass spec separate?
Well, the whole instrument would be just called a mass spectrometer.
Okay. Not
Right.
like a GC.
Well, a GC, if you have GC, gas chromatography mass spectrometry, then essentially the GC is just a sample input device. You can either do, like on EI, oftentimes they use this, direct inlet, or you could have a GC or an HPLC or,
Electron spray or ATC.
yeah.
Okay.
Well, GC
Well-
and HPLC go through a column.
Right. So so the input is different than the actual ionization method, though.
Okay.
Yeah. All right. Let's look at an example here. So I think this comes from our Appendix A in our book. Okay. So there's a big, multi-page table. I think it's at the end of the first chapter. And it goes up, I don't know how high, it goes up to a pretty high mass, and it shows all the different mass or elemental compositions that add to that unit mass. So 138, I don't even know if I got the whole part here, I might have just taken out a piece of it. And notice, they're all, they're the same at 138, but they're different out in the decimal places.
It's a great example to young students like in the 115 and 125 labs
Mhm.
saying sig figs matter.
Yeah, sure. Yeah, right. So one thing about these tables is that I don't think that all of the formulas necessarily make sense.
4 nitrogens and 6 carbons, and that's explosive.
Yeah, you know, or they may have some formulas, I don't know what limitations they put on here, you know, because, you know, and there are programs to do this as well. And you can put limitations or ranges on the different atoms, okay? Do you want to consider the possibility of having a halogen or a sulfur, or do you want to put say there can be a maximum number of a certain atom or something like that? Because otherwise, all it's going to do is go through the atomic masses and just come up with any combination that adds up to 138. Okay? So if you didn't limit at all, you could maybe come up with a number that just is all nitrogen and oxygen or something, or just some, you know, crazy. But, so, you know, you get this kind of measurement, and usually they'll give some masses, and then they'll give a amount of error. So how far is your measured mass away from the calculated mass? And then you'll have a number of possibilities. And so obviously the bigger the mass of the ion you're looking at, the more possibilities there's going to be. Right? So sometimes you could rule out all other ones. Sometimes you're just going to, you know, reduce the possibilities, but there will be more than one possibility, and then you have to, you know, use other data, you know, to narrow it down even further. All right? So, you know, for organic compounds, I guess, just with carbon, hydrogen, and oxygen, you can compare, you know, like C7H6O3 versus C8H10O2. These would be logical types of molecular formulas. And if we look over at the masses, you know, at the second decimal place, they're off, you know, by enough that you could narrow it down. So this is, you know, this is a common way to do this. Of course, to you know, run a high resolution mass spectrometry, it costs more money than if you just do it for a unit mass, because it takes a more expensive instrument to be able to do it. But, you know, this is, you probably do this rather than what we did on the previous one.
I don't think it's high res.
No.
It
Huh?
only goes to one decimal place.
The GCMS here?
Yeah.
Oh, well, the GC.
The ESI,
That doesn't.
The ESI mass spec.
Oh, okay.
That's
if you want
lower
to,
res.
we go to one decimal place.
Okay. Yep. Okay, so that's what we're going to talk about for molecular formulas and molecular ions and stuff. So let's just kind of do a little introduction to fragmentation mechanisms. Okay, so the first thing to remember is that these mechanisms are going to depend upon where the molecule ionizes. All right, and so we already said that the ionization probability goes from the most probable is on the non-bonding electrons to pi electrons to sigma. Okay, and it just based upon how strongly those electrons are being held by the molecule. Right, so in sigma bonds, they're being held much more strongly than non-bonding or pi electrons. Okay, so we're going to look at kind of three types of cleavage here, and then maybe we'll do one more. I don't know if we'll have time today. Okay, so the first one is called sigma cleavage. And this one we kind of already looked at in the beginning. I kind of showed you that. This is just the cleavage of a sigma bond. Okay, so generally what it involves is ionization in just a sigma bond in the molecule. So we drew it kind of like this before. We lose one of those electrons, so we could say we're going to ionize it with electrons. We lose one of those electrons. Okay, so here's our radical cation, and we're just kind of localizing the position that we lost the electron. We can think about this. We just now have a one electron bond, so we weaken this bond, and so this bond can break. All right, but it can break in either of two ways. You can either break with the plus on this side and the radical on the other that side, or it could break the other way around. Oops, I shouldn't have put that there. And of course, like we saw before, which way around this goes, oops, that's the plus, not a, depends, can depend upon the structure, right? So if one of these, if cations is much more stable than the other, then we'll see much more of it. Okay? All right, the next one is a homolytic cleavage, right? So this is a cleavage where we're going to split a bond with an electron going to each side, okay, an even splittage. And so this we can think of as being a radical initiated process. Okay, so out of that radical cation, it's going to be the radical that does the reaction. Okay, and so the way that this goes in kind of a general sense is, for example, if we have some heteroatom, and I'm going to draw it like this, and we ionize on that heteroatom. Okay, so it has a non-bonding pair. It could be an oxygen or a nitrogen or something like that. Then it's the radical. These electrons can be donated down here. It's going to combine with those, and it's going to homolytically cleave this bond that's on the opposite side of the, what we could call the alpha position to that functional group. So if it does that, it's going to go to Y, and it's going to form a double bond here. We cleaved that bond, and we got a radical over here. We still have a plus that's on that heteroatom. Okay, so we've cleaved this bond right here. Okay, so well, we'll look at more examples later. You could also do this from pi bonds. So if we don't have any non-bonding electrons, we only have pi bonds. Let's ionize this. And so then we just have one electron left in the pi bond. And so you can kind of choose which way you want to draw this. I'm going to draw the plus on this side and the radical on this side, but you could reverse those. And then from this, we can draw the same type of cleavage like this. Okay, this is oftentimes called an alpha cleavage. All right, and if we follow those arrows,
So that alpha position radical is just staying where it is and combining with a radical connected to the R1 group, correct?
This one right here?
Yeah.
So it's kind of, the way we've drawn it is kind of localized on this carbon. So it's going down to form a pi bond here together with one electron from the adjacent bond. Right, so we're cleaving this bond here, and we're going to form a pi bond right here. Okay, so what we would end up with is a plus would stay where it was, form a pi bond here, plus R prime radical. All right, so we're forming, in this case, this allylic carbocation as an ion, so that's reasonably stable, right, as an allylic carbocation. Okay, so we'll look at different applications of these too. So, this homolytic cleavage is common for, alcohols and ethers and amines and things like that. All right, so a heterolytic cleavage is where a pair of electrons go to one side, right? So we can have the same type of cleavage if we have ionization on a heteroatom, but this time this is going to be cation initiated. Okay, so it's going to be the bond adjacent to that heteroatom which is broken, and it draws the electrons towards the plus. So if we do this, we end up with Y. We had a radical there, stays there, and we have a new pair of electrons there. So this side is now the radical plus a cation over here. Okay, so in this case, the cation doesn't stay with the heteroatom. Okay, and we're in fact cleaving a different bond, right? The alpha cleavage cleaved the bond one position away, and the charge stayed with this Y group. For this heterolytic cleavage, it cleaves right adjacent to this heteroatom, but the plus goes on the other side. Okay, and depending upon the atom, these two mechanisms can be kind of, well, all of these are going to be competing with one another, right? And if we have a molecule with more than one heteroatom, more than one, or extra pi bonds, then even the ionization is a competition. Okay, so you have a population, it's in some molecules it's going to ionize here, some it's going to ionize here, and we got a whole bunch of competition going on. All right, so let's just finish off with I'm going to have to add an extra slide in here. Cleavage mechanisms.
I'll clap you first.
Okay, so we'll do that. Okay, so here let's do it in a generic sense first. And I'm going to draw this in this special kind of way. I'm going to add just a Y group up here. And it has a non-bonding pairs of electrons. Okay, so when it ionizes, and let's just say that this is the alpha position, right? Alpha, beta, gamma. If we ionize, it's going to ionize up on those non-bonding electrons plus radical. Okay? So now if we have a hydrogen on the gamma position, then we can essentially form kind of a six-membered transition state, and what happens is that the hydrogen atom is transferred over to the Y group. So this can go this way, combine with one of the electrons in that carbon-hydrogen bond, and these electron goes onto the carbon. Right, so now we have a radical is over there. We have Y with an H on it and still has the plus on this side. Okay, and so now we essentially do an alpha cleavage from that radical. So this comes down here, combines with one of those electrons, and this electron goes back over to there. So we get this plus this alkene. Okay, so the important thing to notice here is that we started, like always, our molecular ion is an odd electron ion. And what about our fragment ion? Usually I said we get even electron ions as fragment ions, right? What about in this case? Yeah, we have another odd electron ion.
You're losing an even,
Huh?
because you're losing the even electron.
Yeah, and because we've lost, well, we end up with the radical here and we lose this neutral species, right? And in the process, we've transferred a hydrogen from the side that we would usually lose over to the radical ion. So if we start out with an even mass over here, what are we going to get for our odd electron ion as a fragment ion? Another even mass. Okay, so because we've transferred one hydrogen, right, that ion has a mass of 1 higher. Okay, so let's just stop there. We're out of time. I'll show you a few variations of this next time, and a couple more mechanisms, and then I think we'll be getting to the point of, starting to work through examples.